Hey guys, my name is Max and welcome to Simple Biology. In this video, we're going to be talking about water potential. Now, water potential is kind of a weird subject and it's a little bit more math oriented than most of the stuff we'll be dealing with in biology. But it's very important because it basically determines whether or not a cell will be able to survive in a certain solution, a certain watery environment. And so, because of water potential, we can figure out whether a cell will be able to thrive depending on where it's located. Now, water potential is essentially the tendency of a solution to lose water. So, let's say you have a high water potential that will correspond with losing water easily. Losing water easily. And just the other way too, a low water potential is it won't lose water. So it won't lose water. And so you'll learn how to use that a little bit more later. Next off, water potential is actually represented by this funky looking Greek letter called psi. And it looks a little bit like a trident, so I guess you can remember it by Poseidon holding a trident. He's the Greek god of the ocean or whatever, and so that's water. But that's the symbol that we'll be using to represent water potential. And it's actually the sum of two different values called the solute potential, which is, I guess we can define it as the water potential depending on the solutes within the water, and the pressure potential, which I guess we can define as the water potential depending on the pressure of the solution. And so we've got this nice little equation where water potential equals pressure potential plus solute potential. But let's get into what pressure potential is just a little bit more. Pressure potential is, like I said, it has to do with the pressure that's on a liquid. And it's actually equal to the pressure of the liquid, or the pressure on the liquid, minus atmospheric pressure. So remember this little part, minus atmospheric pressure, because the reason they do this is to make it so the numbers are easier to work with. What this makes it is so that an open container has a pressure potential of 0 bars. So we're dealing with pressure in bars. And this is very important because often you'll have a question that it'll tell you that something's in an open container, but you have to know that the pressure potential for an open container is 0 bars. The reason for this is because the pressure on that container, or on the liquid in that container, is atmospheric pressure, about 1 bar. And so when you subtract atmospheric pressure from atmospheric pressure, you get 0. Now, the interesting thing is you can have negative or positive pressure potential. So negative pressure is like sucking on something, right? Suction. This happens not quite the same way because it's not a liquid, but you have negative pressure in your lungs when you pull down on the air in your lungs in order to suck something, in order to suck the air in. You can also have positive pressure when you push on something. So, like maybe if you're squeezing a balloon, so that it'll blow something out. And just, I guess, if you extend the lung analogy, like when you're blowing out of your mouth, that's positive pressure, where you're exerting pressure on some sort of. In both of those cases, it was a gas, but it would be the same concept for liquid. If you're exerting pressure onto, say, a solution, it'll be like blowing something. Now, next we have solute potential, and solute potential is kind of the more sticky one of the two. It's harder to grasp, but it's related to the water molecules that are stuck in a hydration shell. I'm going to highlight that word, hydration shell. If you remember from when we talked about solutions, hydration shell is essentially a layer of water molecules that forms around anything that will dissolve in water. And so because those water molecules are stuck in the hydration shell, they're not available to diffuse with the rest of the water and to go through osmosis and all that. So it'll be as if there was less water. It'll be as if there was actually less water. So because it'll always be less water, you'll always have a negative solute potential rather than a positive one, which I'll get back into that in a minute. But there's actually an equation that we have to describe solute potential. And there are a couple things that it depends on. Essentially, solute potential equals ICRT. And this will be a very good thing to memorize because it'll come up over and over again. Again, like I said, it'll always be negative. That's where that negative comes from. First off, I is the ionization constant, and this depends on what the solute is. Essentially, there are some solutes that when they dissolve, they'll actually break into 2 or more actual particles. And for them, there will be that ionization constant will matter. It'll always be like 1 or 2, sometimes 3 or 4 or bigger numbers. But it's the ionization constant is the number of particles that something breaks into when it dissolves. So, for example, we have sucrose, which is a very common solute in biological solutions. And it has an ionization constant of 1 because, like all covalent compounds, it doesn't break up into different ions when it dissolves. On the other hand, you have, sorry, that's not supposed to be M. If you have sodium chloride, which is, as you know, table salt, it has an I of 2. And the way you can figure this out is because you got 1 sodium, 1 chloride, that's 2 ions, and so I equals 2. Now, C is essentially the solute concentration. It is the solute concentration. And this will be given in molar, so moles per liter. If you remember that from, let me draw that in. It'll be given in molar, which is equal to moles per liter. And this is essentially just how much of the solute is in the solution. So you might say, oh, I have a 3 molar solution of NaCl, of sodium chloride. Or you might have a 0.02 molar solution of sucrose. Often you'll be dealing with very small molarities rather than like 3 or 4, but that's what the C is for. R is this constant that you'll be given on your formula sheet, and it's equal to 0.0831 mole bars per liter Kelvin. You don't really need to worry about the units, but that's what it is. And this is actually what's known as the ideal gas constant. If you remember that from chemistry, it shows up in a lot of different equations, but it's a constant, and so it'll always be the same no matter what you use it for in that equation. Lastly, you have T, which is temperature, and always has to be in Kelvin. And the reason it has to be in Kelvin is because it can't be. It has to have a 0. I'm not really going to get into it. It has a kind of basis in physics and chemistry. We don't need to know why, but make sure it's always in Kelvin. It has to cancel out with this unit up here, this Kelvin. It has to cancel out with that, and because it has that temperature, the way you can kind of think of it as is when the temperature increases, the solute potential is going to increase, or I guess because it's negative, the solute potential is going to actually decrease. As the concentration increases, you also get a more negative solute potential, and with a higher I, you'll also get a lower solute potential. So that was just kind of summing up what the equation means. Now, the last thing you need to remember is that the solute potential of distilled water is always 0, and it'll be in bars, so 0 bars. So solute potential of distilled water is 0 bars. This is because that is the highest possible water potential you could have. That's the highest. Remember, the tendency to lose water is for a pure water solution, and everything else that has solutes will have a negative solute potential. I hope that all made sense. Check out the quiz below for a couple practice problems, but for now, water potential is really just as simple as that.